Hey guys, welcome to my presentation on our molecular portfolio. For my drug, I was assigned the drug Abilify, and the generic name for that is aripiprazole. And here we have in the middle the chemical name for it. Not going to say that one out loud. For the description, we're going to talk about what the drug is used for. And it is prescribed as a drug meant to help treat manic episodes that are associated with autism spectrum disorder, schizophrenia, and Tourette's. It is mainly prescribed for adults and older kids with schizophrenia. It is also used as an antipsychotic used for those suffering with bipolar disorder. And so some contraindications: don't take this drug if ... For elderly patients, the risk of death is also increased. It can increase suicidal behavior or thoughts. Overall, it was given a black box warning for older patients because they got a higher likelihood of dying if they take it. A black box warning is essentially when the risk of taking the drug is so high for certain groups that the risk needs to be seriously evaluated before prescribing. So you're probably not going to want to prescribe this to your grandma. And so don't mix this drug with, it should not be mixed with other antipsychotics or any drugs that could increase suicidal thoughts, as this could amplify the effects, and that can be very bad. So fun fact, is some patients report impulse control problems, so it could lead you to impulsively gamble or take bad risks. It's not really a fun fact, it's actually a really, really sad fact. I just thought it was interesting because this drug was supposed to help, with antipsychotics and kind of controlling your behavior, but it could lead to some more uncontrolled behavior. All right, so let's start drawing our molecule. So aripiprazole has a couple of 6 carbon rings, and you got some more chlorines attached to it. That's supposed to be a lone pair. And I'm not the greatest at drawing these structures. I actually have never been that good at them. But I'm going to try to draw this quickly to preserve time. And now we have a third carbon ring. This one has a double bond to this area. This second carbon ring, however, that is attached to it does not have any double bonds, which I thought was interesting, and I thought I'd let you guys know. This one has a double bond to an oxygen, and so when we add the lone pairs, we're gonna find that some of the atoms that are not carbons aren't connected all the way for 4. They don't all have 4 connections to other elements, so some of them have lone pairs. Sorry about that. I was running out of time, so I just decided to insert this into my presentation. Already done. So I have the line bond here already done, and instead I decided to just talk about the molecular geometry. Here we have a little chart telling us what each of the colors mean. Here we have trigonopyramidal, and that's when you have 4 electron groups. Keep in mind, lone pairs are electron groups, and when there's a lone pair, it becomes trigonopyramidal. As we see that with the nitrogens, and only the nitrogens. Next, we have the tetrahedral, which is when you have 4 electron groups but 0 lone pairs, and that's the case for a lot of these carbons. We have these carbons that are attached to other carbons, nitrogens, hydrogens. We see that right over here, and along this main chain right here, and at the end of this one as well. And then we have trigonal planar, which is when you have 3 groups but 0 lone pairs. So that's the case for here. Keep in mind that double bonds are lone pairs. Double bonds are electron groups by themselves. So that's 1, 2, 3 electron groups. That's where you get that from the carbons. So that 1, 2, 3, that makes it a trigonal planar. So this one is bent, and it has 4 groups, which is weird because I thought, why is it bent if it has 4 groups? Well, that's just how it is. Bent angular has 4 groups and 2 lone pairs. And that's the molecular geometry. We also have the expanded structure, which has all of the hydrogens attached to it. We don't include the hydrogens on the line bond because we know that they're there, but they take up a lot of space. As you can see, it makes it look messy and difficult to decipher, which is why we have the line bond, so we don't have to look at all the hydrogens. So calculating the molar mass of my drug. So the molar mass of this given molecule, you can find that essentially is in grams, and you can find it by adding up the individual mass of every single atom inside the element. So as you see for aripiprazole, it has 23 carbons, 27 hydrogens, and so on with all the elements. And so you can see the type of math that we use. You have 12.01 is the mass of carbon. You can see all the masses over here. Multiply that by how many carbons there are, and that's how you get this formula. So when you add that all together, you get 448.388. You have to round that to 4 sig figs because of this number right here. This is our lowest number, the smallest number that has 4 significant figures. So we round our final answer to 4 significant figures, 448.4. Hydrogen bonding. This is 11.7. This is our exercise that everyone has. And so you can see that the hydrogen bonding is in a couple of places. We know that hydrogen bonds will occur between a hydrogen and one of the electronegative elements, nitrogen, oxygen, or fluorine. So we have a couple of nitrogen, oxygens, and fluorines. So in cases like here, where there's a hydrogen attached to the molecule, it can still hydrogen bond, but instead of bonding to an H, like these other ones would, it would bond to the oxygen, which is still technically a hydrogen bond. So then we see that in these cases like these, the acceptor is the oxygen, the hydrogen donor is the molecule, and so essentially you have the acceptor, the donor, and that's the case for a lot of these places. And most of the time, the molecule will be the acceptor, but sometimes in cases like this, you have the molecule being the donor. So here we do this again, the hydrogen bonding with aripiprazole. Remember that chlorine is not one of those electronegative elements that hydrogen bonds occur in. So then chlorine doesn't really have anything, but in this case we have a nitrogen with a lone pair that hydrogen bonds to this water molecule. Well, it has the potential to. And you can see that this is the donor. It's donating a hydrogen bond to this acceptor over here. Same case with the O's and the N's. Now we're talking about polarity and solubility. So here I've written all of the polar electronegative elements. The chlorine's right over here, chlorine's over here, nitrogen's over here. So nitrogen is a lot more polar than these carbons that we know is there. And so you can, in most cases, the nitrogen is going to be the more electronegative element, and it will be electronegativity will be heading towards there. Same case with the oxygen, same case with the nitrogen, same case with the chlorines. This case, there's a hydrogen here, but it's still, the nitrogen is still a lot more electronegative, so the arrow will be pointing in that direction. Before I forget, I also want to talk about the solubility of this molecule. I predict that to be relatively insoluble because there'd be no ions to dissociate into water. It's also a relatively nonpolar molecule. There are some polar aspects of the molecule, but a lot of that gets canceled out by the different directions of the polarities. And according to PubChem, it has a 0.00001% weight to volume solubility, which is basically insoluble. It means it's pretty much not going to dissolve in water. And let's talk about solution calculations. All right, so first of all, we're going to calculate how many grams of the drug you'll need to weigh out. And so we're already given the amount of solution that we want and the molarity of it. So we just need to figure out how many grams that would be. So first, what you're going to do is you're going to find how many moles that is. And we find that it's 0.0115 moles. And after that, you're going to convert moles to grams. You're going to use your molar mass of the solution, and that's going to be equal to 1 mole. So then when we multiply across, and after we're done rounding, we're going to find that we have to use 5.16 grams of aripiprazole. Then after that, you're going to place the weighed out drug onto a properly cleaned volumetric flask. You're going to clean, by properly cleaned, I mean you're going to use soap water, followed by tap water, followed by ultra clean DI water. And then you're going to fill the flask with deionized water all the way up until the 50 milliliter line. And then you're going to revel in your accomplishments because now you have your 50 milliliter solution of that right molarity. Of course, you're going to stir it, but yeah, if it was soluble. Now, we're also going to talk about how many milligrams of the drug are contained in 2 milliliters of a 3% solution. So we're going to find out how many grams of solute that would include. And so once we follow this formula, we find that it's actually going to be 0.060 grams of solute. And so we're going to convert grams to milligrams next. And so we're going to find that 0.060 grams of aripiprazole times that little formula for converting milligrams to grams. We're going to be left with 60 milligrams of aripiprazole. And that's going to be rounded to 2 sig figs because this is 2 significant figures because that is 2 significant figures. All right, that's it. That's my presentation. Hope you liked it.